Okay, maybe I'll start on this side today. So yesterday, I tried to give an idea of what is renormalization in parabolic dynamics and why is it useful. So maybe I will just write a quick philosophical recap. So we have some renormalization operator, and you can think of this on a flow as something which contracts long trajectories of your flow, and or induce or zooms on smaller scales if you have a discrete dynamical system. And somehow the main idea is that this works well when you have a self-similar kind of system. When your system, various scales are self-similar, this corresponds to fixed points, fixed or periodic points of renormalization. So if your dynamical system is fixed, or after finitely many iterates, okay, you can just accelerate and replace it with the power, then you have a self-similarity between different scales. This is quite rare, but somehow what is quite common in these parabolic worlds is some form of almost self-similarity. So, and in this case, maybe your system does not come back to itself. So, and this R, you can see it as acting on a class of dynamical systems. And again, yesterday, as an example, we had the linear flows on translation surfaces. So it's quite rare to have a linear flow which is really fixed, but it's typically, if you have a linear flow, it will not, when you rescale it, it will not go back to itself, but it will come back to a nearby linear flow, which is a small perturbation of the surface and small perturbation of the direction. So it's almost a self-similarity. You can see it as recurrence. This corresponds to recurrence. So you start from a dynamical system in your class, and your renormalization brings you back close to it. So this is a wider point of view. And this is what I said yesterday. What I wanted to add to this philosophy is that it can also happen. So renormalizations which are useful usually are indeed recurrent. But it could happen that renormalization diverges, so that there is some kind of degeneration. Degeneration between different scales, and this is kind of corresponds to divergence of renormalization. In this case, renormalization is not so useful, even though I'll mention an example where you can still sometimes do something. But and somehow the last step is that if you can have somehow your class of dynamical system, you can put it in a space. It can be described by moduli space, and sometimes this space is not compact, and you can have faster degeneration. So you can kind of escape, for example, at linear speed into the non-compact part, and this somehow corresponds to for example, when you have periodic orbit, let me just give you this example just to understand. For example, to explain the last part, for example, if we go back to our linear flow on the torus, or even our linear flow on the octagon, yesterday I chose some special directions which were self-similar, but also were in particular irrational. So if you take, for example, a direction theta which is rational, then your flow is actually completely periodic. So all trajectories will be periodic. And if I start doing what I was doing yesterday, so shrink the direction of the flow, I'm actually shrinking on my flow. I have some periodic trajectories. And when you shrink this periodic trajectory, actually your torus is somehow degenerating, in the sense that these trajectories are becoming smaller and smaller, and it's like you're pinching some kind of curve. And similarly here, you can see that somehow the degeneration corresponds in particular to some pinching of some curves, and then in your space of translation surfaces, you are kind of not recurrent, but escaping to some non-compact part. OK, this is just a meta picture to finish off from yesterday. OK, so yesterday I just mentioned the special case of the octagon, but indeed I want to state some much more general theorem which has been proven on deviations of ergodic averages, which exploits the ideas from yesterday. And this is the following result. So I'm going to consider now a surface. And again, you say much more general than yesterday, so I just want it compact, connected, orientable. And it's a smooth surface. And I'm going to consider a flow, let's say phi r. And assume that this flow preserves a smooth area form. Preserves a smooth area. I will call it mu. So again, you can think, I don't know, this could be also a symplectic manifold, and then you can have area form, dx dy, and smooth just means that you have, so for example, something that locally you can write as some, I don't know, let's call it h, x, y, dx dy, where h is smooth. And the flow preserves area. And OK, so this is also something which is, again, they also call the locally Hamiltonian flow, because a flow which preserves area locally, you can see it as a Hamiltonian flow, but maybe I'll skip this. Actually, these locally Hamiltonian flows were the topic of, I taught a course here at THS in the other room 3 years ago, which was all on mixing and properties of locally Hamiltonian flows. So this is the example on my list on parabolic flows on which I want to spend the less time, because if you want to know more, you can watch the recordings of the course 3 years ago. But I will tell you something about these flows also tomorrow, and I will tell you something recent that happened after the course, so in the last 3 years. OK, but so this is the setting now. And sorry, where did I have the page? Yeah, OK, stop here. Oh, it doesn't matter. I'll improvise. OK, and so what I want to say that this flows actually, and then I take a function s from R, and now I can really I can write smooth. And so I have a smooth function on my surface, and I'm going to consider, as we did yesterday, the ergodic averages along the trajectories. And what I want to say is that indeed this ergodic average display power. OK, and I'll tell k to me means 0. OK, well, actually, sorry, I would like to find my notes, and I lost them. OK, maybe it does really not matter. OK, so what I wanted to, maybe let me put it, yeah, let me put it here. So this is a theorem, and I'll then attribute it to several people. So I'll tell you the references at the end. And so what I want to say now is that for, OK, I'm going to, I will need to assume that this flow is uniquely ergodic. So that, and what I want to say, and sorry, one more thing. OK. The genus of this surface is some g, say greater than 2. And maybe I will put first a remark that actually when you have a flow on a higher genus surface, you necessarily have fixed points. So if the genus is greater than 2, in particular, the fixed points of this flow are the set of fixed points is not empty. And So if the flow is uniquely ergodic, in particular it is minimal, so orbits are which are infinitely defined are dense, and you can show that the only type, because of minimality and area preserving, so fixed points are of saddle type. So the fixed points of your flow could be saddles, and these typically are simple saddles. Or they could be degenerate saddles. So they could also be saddles with more than 4, these are called separatrices. And there could be more than 4 separatrices, but always an even number since it's a flow. Or degenerate saddle. OK.
Just very quickly, self-fixed points is non-empty. You wrote equal empty. I think you mean non-empty.
So this is a simple Hamiltonian set. Sorry?
I mean, for the fixed point set, you wrote equal empty set. But
it's a different than empty set. Sorry. Maybe I said it's not empty. Absolutely. Yeah, so you're forced to have by genus and Euler characteristic constraints. You're forced to have singularities. And these singularities, indeed, can be saddles. And there is also a relation between the number of saddles and the genus and the prongs on each saddle. So, OK. So I'm going to fix the genus and number and type of saddles. So by type, I mean the number of prongs of each saddles compatibly with the genus. And then what I'm going to write is a theorem. And as I said, maybe let me write already. I will tell you what is the contribution of each. So it's Forni, it's Zorich, it's Forni, it's, OK, maybe let's start with Zorich and Forni. And so what I want to say that there exist some exponents, alpha 1, alpha g. And actually, maybe I will even write alpha 1 is 1 greater than alpha 2. And maybe let me put Abilaviana also here. Alpha 1 strictly greater, which is 1 greater than alpha 2, strictly greater than alpha g, strictly greater than 0. So I want to say that ergodic integrals display power deviations, but the powers that appear are only one of these g possible exponents. And give me 1 second. I really should find the statement how I wrote it in the notes. No, I forgot it. I really forgot it. Yeah, I don't know where I put the page. Doesn't matter. OK, such that and now here I have to lie. So I will tell you for almost every flow, and almost every, I cannot define exactly. So there is a way to put a measure on the space of this smooth area preserving flow. And this is measure class, actually. It's the Katok fundamental class. Measure class. And it kind of depends on periods of this flow. You can integrate your OK, I don't want to define. So there is a notion of measure, and you have to take typical. So in particular, a typical one will be uniquely ergodic. And this almost every measure implies, in particular, that they are uniquely ergodic. Such that, so for every function, we've said already C infinity smooth on the surface, we have an expansion of this form. So the integral, and for all, let me write almost all points, my ergodic integrals. OK, now I don't want to write, let me not write that is integral 0. Let me just put the first term of the expansion will be, in general, the integral times t. So if the function is not with 0, then the first order, it grows like integral times t. And then there is second term, which I will explain. Maybe maybe let me just write C2. No, let me just write T2 of f. And then I want to write, I will as the final notation. Let me write something which grows like O to the alpha 2 plus dg f O of t alpha g plus an error, which is small o of t to the epsilon for every epsilon. So what I want to say that there is some kind of expansion where the first order is linear in T, and these other orders display g possible ways of having power deviations. And what do I mean by O of T? So the term here, so O of T to the alpha, so let's say, this means, maybe I should have written, I think I should have taken my notes. So this is, I mean, here there is a function which is OT, so maybe I should have written G2 of x, G2 of, OK, so what I want to say that here there is a function which is big O of t to the alpha, which means that this expression that I have over there, when I divide it by, do I still have the eraser somewhere? OK. Shortcut for expression such that when I take the log and I divide by log t, I want to say that it's something which has a fluctuation of order power t to the alpha. So, and what I really mean that if I take the lim sup in t of log of my expression divided by log t, this is equal to alpha. So this is a way to say that you have a power behavior. So if you have exactly a power t to the alpha, when you take log and divide by log t, you go to alpha. But you are allowing some sub-polynomial extra terms, some logs or some extra. This is just a formal way to say that this quantity grows like t to the alpha plus some lower order terms. And it's not really, it's a lim sup that it's infinitely often. It has the size of t to the alpha. So, OK, so, and the other thing I wanted to say, what are these di? Di are distributions. So they go from C infinity of S to R. They are distributions. So somehow each function will give you, so for example, if for typical functions, so for most functions, for most functions, most functions, OK, most function will have integral on 0. With most functions with integral of f is equal to 0, you will see d2 of f will be different than 0. And then you will see that the ergodic integrals have indeed gross O of t to the alpha 2. And this is somehow this alpha 2 that we saw yesterday. But you could choose, there are finite codimension subsets. So you could, so the first codimension is integral 0 and kills the linear term. And typically you will see this fluctuation of alpha 2. But then maybe you can find a codimension 2 subset of functions for which d2 is also 0. And then you see alpha 3. And you can maybe kill g if you're in the kernel. So if your function is in the kernel, so if f it's the kernel of di is the intersection of the kernel from 1 to g, then the fluctuations are actually subpolynomial of t to the epsilon for every epsilon. Yeah, actually, maybe the last one is small o. So, because it's not the same notation. It really means it's less than t to the epsilon for every epsilon. OK, so this is what is called, so this type of behavior is what is called the deviation spectrum. Maybe I should write it here so you can still see. So this is called deviation spectrum. So ergodic average is displayed as power deviation spectrum. So sorry. Power deviation spectrum with this power. And so who is this result due to? So this, first of all, it's a conjecture. So that the smooth functions, ergodic integrals of smooth function for an smooth area-preserving flow is indeed a conjecture which was formulated by Kontsevich and Zoric in the 90s. So this was Kontsevich-Zoric's conjecture. And the first person who proved, who proved somehow this term, the first deviation, is indeed Zoric. So Zoric in 1997, so he proved it for special functions, and this is what I was trying to explain yesterday. So for special function f, and it's actually not exactly in the setting of a smooth function in this case, but it's a function given by intersection number, by cohomology class. So you should think of given by some intersection number with some curve. And this is the case which yesterday we were discussing corresponds to functions which are locally constant on some interval. So when you have these special returns, all the special returns give you the same value. So this is kind of the easy case. Not easy, but it's the case fully determined by linear algebra, essentially. And this is also for alpha 2 only. But this phenomenon that I think he discovered experimentally then prompted the conjecture. And the conjecture was essentially proven by Fourier in 2002. And Fourier, but maybe I will write something. He puts an assumption that f is, in the case it's really a smooth function, but the support of f is contained in S minus the fixed points. Or more in general, for Sobolev function, he can also, it's not necessary to assume that the support is strictly contained far away from the fixed points, but then you still want your function, or at least if it's a Sobolev regularity, you want that f is actually 0 on every saddle, on every fixed point. Okay, so and then there is, OK, and Fourier also proved, it was almost a full proof, but with actually inequalities. So he could prove that there are g exponents which are strictly greater than 0, and that's an important part of his work, but he couldn't prove that they are distinct. So he only had nu g strictly greater than 0, but only nu I plus 1 greater or equal than nu I, and not necessarily distinct. And then there was Avila and Viana completed this conjecture by showing the simplicity, so that these exponents are indeed distinct. So there are really g distinct exponents. And again, I will say a word about these exponents, where they come from. And the other thing, there's a small case left, which is what happens if you really want to go to the original setting of a smooth function. There is no assumption that the function should be 0 at singularities. And in this case, actually, there is a recent improvement. So maybe I should have, OK, maybe I should have said before I say that, let me also add the work of Buffetov. So Buffetov has proven a refinement of this conjecture. So he has given a more precise description of how these functions oscillate. So maybe I will just say some kind of asymptotic expansion. He had defined some cocycles which have oscillation of this order, which is really, he has some information on the functions that go inside this big O. Okay, maybe we'll put it in parentheses because it's not strictly. And then let me go back to, so Krzysztof Franczek and myself recently, this is only a preprint of a few months old, we have considered the case where indeed we allow F to be non-zero. So general case, let me just say, general case of F smooth. So allowing the function to be non-zero at singularities. And in our paper, though, we restrict to the case of simple saddles. And in this proof, we also give a new proof, which is not the same method than Forni, but uses a work by Marmi, Musa, and Yokos on the cohomological equation. Maybe I will, okay. Marmi, I forgot Musa. Marmi, Musa. So it's a different proof of the result. Again, using renormalization. I must say that already Forni uses renormalization through the proof of Forni is very much in the spirit of what I was trying to explain yesterday. He uses a continuous form of renormalization by rescaling arcs. And the proof using Marmi, Musa, Yokos is more using a discrete version of renormalization, which zooms on the Poincare maps. But OK, I will not go into detail. And finally, Min-Sung Kim. So Kim, F, K is after F. Franczek Kim. Franczek Kim have done this case for also degenerate saddles. And when you consider the degenerate saddles and the function which is not zero on the degenerate saddle, actually this result is not correct. You need to add extra polynomial terms. So there are not only these G powers, but it's quite interesting that there are additional power exponents which depend on the saddle only and not on the function exponents. Okay. Okay, so this was just a bit of history of deviations of ergodic averages in this context. And what I wanted to say is also, I do need that eraser now. Sorry. Thank you, fantastic. Yes, so a bit of sketch, but even though sketch is a big word, I just want to say something. Because I do not want way too technical for this course, but I want to say that the ideas behind the proof of this result indeed are very, I hope yesterday I've given you the simplest possible case, but I want to say that somehow it contains the germ of the idea of how to prove this in general. So I just say a few words on the technique. So it is a general case of smooth flows on surfaces. Preserving a smooth invariant measure can be actually reduced to the study of linear flows in the following way. So if I have this smooth invariant measure, so one can choose coordinates. I can choose good coordinates such that the flow you want to study, phi r, smooth error preserving flow, is actually a time change of a linear flow. Of a linear flow on a translation surface. Or maybe I should say, well, it's isomorphic too. So, OK, choosing coordinates is OK. You can build an isomorphism in which this flow becomes a time change of a linear flow and on a translation surface, indeed. So you have some And again, I'm in the assumption that the flow is minimal, so uniquely ergodic and minimal. So if it's minimal, you can do that. If it's OK. And there is a problem, though. So time change we saw. So it means it has the same trajectories than a linear flow, but the time parametrization is different. But there is a little problem that actually, so if the support of the function is far away from the fixed points, from the saddles, maybe I should say something. Maybe I'll let me say something. So the problem of this time change that it's only smooth outside, far from outside neighborhoods of fixed points. So if I am at epsilon distance from the fixed points, this time change is smooth. But actually, this time change is very singular, or kind of blows up, or slow down. It depends if you take one of the inverse. Blows up near saddles. And the reason is kind of simple, that if I have a saddle point and I'm flowing on linear trajectories at unit speed, like we do in a linear flow, if I'm moving on linear trajectory at a unit speed, I will reach this saddle in finite time. If I'm moving linearly, I can reach the saddle. But if in these smooth flows, which are somehow Hamiltonian, it actually takes, so linear flow hits the saddle in finite time. But my smooth flow, phi r, basically if I'm moving along a separatrix, it takes me infinite time to reach this saddle. So phi r takes takes infinite time. So so this somehow the time change, the time to reparameterize should explode at the saddle, because instead of getting there in finite time, it takes me infinite time to get there. And this creates a bit of issues in the reduction. So if the function that you're studying is supported far from the fixed points, then you can really reduce the problem of smooth flows, smooth error-preserving flows. You reduce to study really ergodic integrals, let's call it G to give it an afferent name, along linear flow and in suitable class of functions. But if your function is non-zero at some saddle, then you have to pay, maybe I cannot say too much. Then you don't have this reduction immediately, so you need to work with singular functions over this flow somehow. And this is somehow the improvement that we do in the work with Shistov and in the work with Kim. OK, but nevertheless, you can kind of reduce to study linear flows. And when you study linear flows, you can use the technique that we saw yesterday of building some special trajectories that you control, and then controlling those using matrices. But maybe, so then, maybe I'll say one last word, and then I will move on a new topic. So for general linear flows, so yesterday we saw fixed point. So we saw the special case of the octagon, and we had a fixed point of renormalization. We had a matrix B, and we have the same matrix we have a matrix which described the action of the diffeo in homology, which was governing everything. In the general case, you don't have one matrix, but so you have a surface, you renormalize, and you come back nearby to a different surface, and you can still identify homology classes if you're sufficiently close, and you can still build these longer and longer special trajectories, but somehow at every return you get a different matrix. So the return is not given by iterates of the same diffeo, but you get a sequence of matrices. Sequence of matrices. Let's call them Bn. They are all symplectic matrices, actually, and they all in SL say 2G, comma Z. Actually, it's incorrect. It's 2G plus cardinality of the fixed points. OK, it doesn't matter. Maybe let's write. No, if it's absolute homology, it's OK. So you get a sequence of matrices which describe changes of base in homology. So it's not the same matrix, but it's a sequence of matrices. And this matrices actually is what is called Kontsievich-Zurich cocycle. And if I have a single matrix and I look at iterates of this matrix, I have eigenvalues, so positive, no, greater than 1 or less than 1. And here you have to replace eigenvalues. If I have a product with matrices, the object which generalizes eigenvalues are Lyapunov exponent. So yesterday we saw that the deviations were given by somehow the second, or somehow the relation between the first and the second positive eigenvectors. Sorry, not eigenvalues. Oh yeah, eigenvalues. So yesterday we had so alpha yesterday was somehow related to, so it was lambda 1 to the alpha was equal to lambda 2. So alpha, if I take log, it's the log of lambda 1, lambda 2 over log of lambda 1. So it was a ratio of logs of eigenvalues. And here, the objects which come into play are ratios of Lyapunov exponents. OK, this is all what I want to say about deviations for this setting. OK, so maybe there is one more I want to say indeed. So this is great for flows on surfaces, which are indeed one of the main examples of parabolic flows. But where else can you do something similar? So in some sense, maybe I will do a bit of summary. Here. So, OK. So there, maybe I will say something. Another case which can be treated similarly, another case which is renormalizable. And a nice case is also the one of Heisenberg-Neel flows. OK, maybe I will. So I talked about them last week, but yeah, maybe I just want to say, so this is, again, it's a quotient of the Heisenberg group by a lattice. And then you look at some one-parameter flow on this quotient. And in this case, you can also prove that these are renormalizable. So maybe I'll just say one word. So this Heisenberg group has generators x, y, z of the Lie algebra. X and y give z, and x, z, and y, z are equal to 0. And you can kind of define somehow the space of all nil flows that you want to work with is actually so somehow, okay, maybe I will go into say, you can identify the space on nil flows with what is called ASL to R modulo ASL to Z. So ASL to R. Okay, so these are matrices of the form, what are we doing? Well, it depends on which way do you do. Okay, you can, these are, it's a matrix in 3 by 3, where here you have a 2 by 2 matrix in SL2R. And here you have 1, here you have 0, and here you have a UV. And UV are real. So you can kind of identify, you can kind of imagine to study change of basis in your, you can deform your nil flow by changing X, Y, and Z, and looking at deformation which is fixed in the center. And okay, deformations are given by SL2C mod SL2. Okay, maybe I cannot explain this in a brief time. Okay, but maybe the picture that I want to draw, that here too you have a space, the space of all Heisenberg nil flow, and you have a renormalization. And this renormalization now is given by somehow changing your generators. So the renormalization takes X, Y, and Z, and it maps X to, okay, imagine you want to study the flow in direction X. I can always assume that I choose X to be my generator or my flow, and then you want to renormalize something like this. E to the minus t, e to the ty, and z you don't move. So it's somehow the renormalization similar to what we saw yesterday, where the direction of your flow is shrinked, and then you want to preserve volume, R measure, so you have to dilate the orthogonal direction, and you do nothing in the z. And actually, this renormalization turns out to act as, so this renormalization is recurrent. So for almost every nil flow, if I do this renormalization, I live in this space, and I come back close to where I started. So this is another example of recurrent renormalization. And this renormalization is essentially just a geodesic flow on a torus extension of the modular surface. So okay, you understand, everything is very explicit, you understand it very well. And this renormalization was used by Flaminio and Forni to study gross over ergodic deviations over ergodic averages, to prove some kind of polynomial deviations over ergodic averages for nil flows. Okay, so this is again a situation in which you can use some of the same. So again, in the philosophy, that when you have a good renormalization that you understand and is recurrent, you can use it to prove quantitative results on ergodic integrals of the parabolic flow, which is renormalized. And yeah, what else did I want to say? Okay, maybe, unfortunately, not all parabolic flows are renormalizable. So maybe I'll finish this part with renormalizable parabolic flows. With the summary. So what is renormalizable, what is not? Okay, So maybe I will do renormalizable and not renormalizable. Oh, well, we don't know how to renormalize, maybe. So the horocycle flow is renormalizable in a trivial way, because we saw yesterday that when I renormalize, the geodesic renormalizes the horocycle. So somehow it's the simplest case because I don't need a class. I just take the flow itself and the geodesic renormalizes. But if I go to higher dimensions, so unipotent, so here I'm in dimension 3. I have stable, unstable horocycle and geodesic, which renormalizes, say, the stable or unstable horocycle. And, or stable, depends on which direction you go with time. But here, if you go to unipotent flow on some G mod gamma in homogeneous dynamics, Lie group, semi-simple Lie group, and okay. Or you can also think, somehow, the problem is that you have a notion of horosphere, and the horospheres are the stable or unstable manifold of some geodesic flow. But your unipotent flow is one-dimensional in a higher dimensional horosphere. So it's actually, you don't have an easy way to, and indeed getting quantitative estimates is much harder. So just the other day there was a talk by Elan Lindenstrauss, who was proving some quantitative equidistribution estimates for unipotent flows. Unfortunately, I didn't hear it. Okay, so but this is somehow, okay, horocycle is good, unipotent is harder. And then here, also good, we just said we have Eisenberg-Nil flows. And again, here the renormalization is very clear. You have a nice space and the renormalization which you understand very well. And you can use it for quantitative results. Great. But if you go to nil flows, so on, let me write higher step. So the Heisenberg group is step 2. So if you take commutator twice, okay, step of a Nil flow. So this is the step of a Nil flow. So if you have a Nil flow of higher step, then actually, again, we do not know how to renormalize them. So there is not such a easy, nice renormalization. And indeed, it's much harder to get actually quantitative results. So maybe I will just mention that for a special class, what are called quasi-abelian or filiform, and maybe this I will say if you were here last week, these are things that you represent as a special flows over a skew product on Tn. So yesterday, last week, we saw that the Heisenberg flow is a skew product over, it's a special flow over a skew product on T2. And similarly, there are family of Nil flows, which you can write as special flows over skew products. And those, again, it's Flaminio and Forni, have tried to renormalize them, but they've tried to do something similar to what we do here, but the renormalization diverges. So you don't have recurrence, diverges, but somehow they still manage to exploit a divergent renormalization to get estimates on equidistribution. So if you can control the renormalization and it doesn't diverge too fast, if the generation is not too fast, you can still exploit renormalization. But in general, outside this category, not even that is, so we don't know. So maybe let me write it, don't know how to renormalize. I would like to say not renormalizable, but maybe we just didn't come up with a good way to renormalize them. OK. And the last in this picture, so I call it the 3 categories that we are discussing mostly in this course are horocycle flow, nil flows, and then we have flows on surfaces. So yesterday I said linear flows on surfaces are renormalizable. And we saw today that you can also use them to study smooth area-preserving flows. That up to time change, even though singular time change, you can reduce and still use renormalization methods. So this is great. What is not renormalizable if I have a smooth flow, which without assuming not necessarily area preserving, necessarily area preserving, smooth preserving a smooth area. Then somehow, okay, then it's kind of a question of which ones are renormalizable, and somehow being renormalizable, it's somehow equivalent to being C1 plus alpha conjugated to a linear flow. Okay, maybe I will leave it open, but somehow, so here somehow you can define some form of renormalization, but RT typically, some renormalization typically diverges. Maybe to make it more serious, because I cannot say, I should say, if anybody will watch. And no, so this is the relation between generalized IET versus interval exchange maps and generalized IET conjugacy questions, which is behind. And there is some recent work, and also, well, Jacques-Christophe Yocoz started all this area of research on kind of understanding this type of renormalization question in this setting. And okay. And recently, I also started working with Selim Ghazouani on this question, and it's kind of a nice setting where there is some form of renormalization, but typically renormalization diverges. So you're kind of trying to find the dynamical systems for which there is convergence of renormalization, or, okay, maybe very vague. Okay, this, yes?
About kind of for this last setting, kind of mimicking the stuff from above, if one were to look at a smooth flow in higher dimension, but which preserves a symplectic form.
That I don't know what to say. So I don't have, it's a good question, but I don't know. I know. Yeah, it's a good question, but I cannot tell you anything. Yeah. Okay. So this was just a picture about renormalization. So hopefully now you know what I mean by, renormalization in this context. I hope you have a good picture of what it means to me. And yeah, it's okay, so now I want to change topic. Maybe it is the good time to have a break. So it's let's have a 5 minutes break, and then after I want to, yeah. So far we saw last week mixing via shearing, important parabolic feature, and the last lecture and a half was about renormalization and deviations of ergodic averages, of power gross of ergodic integral. And now I want to move to the topic of cohomological equation, but it's another feature of somehow the existence that the time changes often in parabolic dynamics produce genuinely new systems. So this is another key feature of parabolic dynamics, which doesn't exist in elliptic and hyperbolic world. So I want to give you a glimpse of that after the break. Okay, good. So let me, again, not everybody was here last week, so I'll try to remind something, but I'm using some. Okay, so last week we talked about time changes of a flow. So I'll recall you, so if I have a flow, say phi r, you can look at time change, So this is a flow which has the same trajectories but new time. So if I go for time phi tilde of t is phi at some tau of x is some phi of tau xt of x. So I'm moving on the same trajectory with a different time. So it's the new flow flows along the trajectories of the old flow, but the time has been changed. Okay, so and I said something like in parabolic world, very often when you time change a flow, okay, we also saw an example that sometimes you can have, it can happen that you time change the flow and you get a flow that it's isomorphic. So let me also recall that the flow and the time change flow are isomorphic if I can find, so there are flows on some x. So x is my space, and they are isomorphic if you find some, now I need another letter, phi from x to x, such that that intertwines the two flow. So phi t, so sorry, phi t of x is equal to phi of phi tilde t of x for every x and t. Okay. So given a time change, it could happen that it's actually isomorphic to the flow I already had. So you can just imagine of this as some kind of change, some isomorphism which connects the two flows. But I said in parabolic dynamics, very often time changing produces genuinely new flows, so flows which are not isomorphic. So what I want to do now is to explain why time changes are often not trivial, so not. So let me say, let me use the notation trivial time change. Time change if phi tilde r is isomorphic. And let me just write. So in parabolic dynamics, there are many non-trivial time changes. And this is related to the issue of cohomological equations and obstructions to solve the cohomological equation. So I want to explain in some baby example where cohomological equations come from, what they are, and why there are obstructions. Okay, let's try. So first of all, let me go to the setting, a nice setting. So let me go into setting of special flows. So this again, I'll remind you for those who weren't here last week. So if I have a flow, I can do this reduction of finding some kind of section to my flow. So I can take f, I can kind of discretize my flow by fixing a section, and I can take f, okay, I can take, sorry, let me write it like this. F, and I wanted x, but okay, let me write y. So x from y to y is a map. And you should think of it as the Poincaré map of your flow. So for example, and I'm going to look at flows which you can represent as a special flow over this map. So again, I have a map f of y, and then I give myself a roof, phi, a function phi from y to r plus. And I'm repeating from last week, but try to catch up with. So I think of this positive function as a roof, a ceiling, and now I define the special flow over f under phi as a flow defined on. Maybe I would. Last time I called it in some way, but maybe I want to have a. Let's use phi. Phi, which I don't know, it's phi of f phi, is the special flow over f under phi. No, sorry, bad letter, because these two look too similar. Let me call it phi. I have too many. I don't have enough letters because phi was the isomorphism here. I need another letter. Can you give me a letter which is not? I want a flow, but I don't want. Psi. Huh?
Psi.
Psi. What is psi?
The triton.
Ah, yes. Very good. This one.
Yes.
This I didn't use. Very good. Okay, thank you. Okay, psi. Yeah. So okay. So this is the special flow. I will get confused soon, but okay. So this is defined. I don't want to write everything because I defined it last week. So maybe I will just repeat. It's defined on the region of space under this graph. So it's defined on. Have you seen it in your life? No. Special flows. Okay. It's a way to extend the map, adding an extra dimension. So now you kind of, it's basically, maybe some people have seen mapping torus. Or, okay, it's a flow on this region under the graph where you move, it's just a the vertical flow. So taking a point, you move vertically up until you hit the roof. And then you go back to the base, applying the function phi. So you start at some point, maybe I should call it y, but okay. You start at some y, and here you go to psi of y, and when you so this is y psi of y, and psi y you identify it with f of y, comma 0. So, or maybe I will write one word. Sorry. Oi, oi, oi. This is too high.
I think we both know the mapping torus. So.
Okay, it's like the mapping torus, so that's good. So it's you flow, but it's flow vertical up and glue the top of the bottom through the map F. Excellent. Okay, so this is a special flow. And again, if you have a Poincare recession, if your map is a Poincare recession of a flow, it's a general construction. You can represent your flow as a special flow over the Poincare map. And the roof will be the return time. So it will tell you how long it takes you to come back to the section. So it's a quite standard construction. And we defined it last week. So now let's assume, and we also saw last week, the time changes of my flow phi r, no, so, sorry, of special flow over f under some roof phi. So maybe I will call it, okay. Time changes correspond to, are also special flows. Are correspond, if I time change, you get again our special flow over the same map. So if I time change, the trajectories don't change. So the Poincare map, the transformation f doesn't change. I'm just changing the return time. So under a new roof. So again, special flow over f under a new roof, phi tilde. Okay, so if I have a flow, it has a representation. A time change has a representation of the same type with the new roof. So the question of when the if two flows have a special flow representation over the same f, when are they isomorphic? So let me write this little lemma. I think I mentioned it also last week, but I do want to sketch it today. So okay, maybe, so which letter am I using now? Psi1. Yeah, so we have Psi1r, Psi2r, special flows over f, of the same f, under roofs, respectively, phi1 and phi2. So if I have, then if there exists u from, okay, y to r such that psi2 is equal to psi1 plus u composed with f minus u, So if I can solve this equation, if the difference between these two roofs can be written as u composed with f minus u for some u, then these two flows are isomorphic. Okay. So I will prove this lemma just to, I will prove, I will not prove, I will sketch the, I will do a bit of a proof of this lemma just so to make sense. But let me say first some name. So notation, or maybe names. Okay, notation. So, so if you bring phi, so if this form of equation, so this equation of u composed with f minus u is equal to phi. So in our case, we had phi, which is, I want to write the difference. Yeah, so I want them bringing on the same side. So if I give you phi, which is the difference of the two roofs in my example, and I ask you, this, can you find u such that this is called it's called a cohomological equation. And maybe I will call it star. Okay, maybe let me write CE for cohomological equation. So, and then, so another notation, so an expression of this form, u composed with f minus u, is called the coboundary. So a function which can be written as u composed with f minus u is called the coboundary. And yes, and u is called the transfer function. Okay, so this is just some nomenclature. I'll keep it aside. So okay, now let me sketch the lemma. The lemma is kind of a motivation to explain why cohomological equations have to do with triviality of time changes. Okay. And maybe the lemma, I don't want to, it's not difficult to do a proof, but it's maybe to prove it formally, maybe it takes me too long, but I just want to convince you, give you a sketch. So some sketch, maybe I will do a bit. So the idea is that if I want to conjugate these two, so to find an isomorphism, I have phi1 and I have phi2, some other proof. So this is psi, what did I call it? Phi, I forgot the letter. Phi 1r, and this is phi 2r. So the idea I will try, because they have the same Poincare map, the same base transformation, I will try to look for an isomorphism of a special form. So I will try to preserve vertical fibers. So if I want to conjugate, because they already have the same section, I'm happy to basically use identity on the coordinates. So I just need to adjust time. So I'm going to look for isomorphism. And now I forgot what was the letter for isomorphism. What did we use above for isomorphism? This was bad. Because, it was var phi. Okay, isomorphism phi from, and now I need a letter. So we are using y for annoying choice. Okay, but this is y in the base, and maybe I will use z in the vertical. So phi, which preserves fibers, vertical fibers, maybe vertical fibers, or z fibers of the form, i.e. of the form y z goes to y and z plus u of y. Okay, I should write it modulo the equivalence. Yeah, this I should think of as an equivalence class modulo. If u is too big, you have to bring it down to the. Okay, so this is in my space that I didn't give a name to. Okay, but I'm just trying to kind of move the y, and again, because indeed I don't want to. So, okay, so let me just show a bit. So I want to just. So let's. I want to convince you that if you have this relation, then you can find an isomorphism of this form. Where u, and so if u claim is that if u satisfy is a solution, it's a transfer function for this cohomological, satisfy the cohomological equation. Yeah, we call it cohomological equation for phi, which is phi. Yeah, this is the content of the lemma, phi2 minus phi1. I claim that it's an isomorphism. Phi is an isomorphism. Oh, maybe I need to go up. Maybe I can also go up like this. Oh, sorry. This goes up and this comes down. And okay. So I'm confused because I changed all the letters compared to my notes. So we want to show that the isomorphism is phi, and this is the flaw is C1t of x. And let me just verify it at the base. So let me start from, say it's not a general case, but okay, let me start from the base. I start from y0, and I want this to be psi2, and I hope I did them in the right order. I hope I didn't exchange 1 and 2, psi2 of psi of y0. So I want to prove that this is phi, the isomorphism. Yes? So I'm just going to yeah, I'm going to lie a bit, but it's okay. So okay, let me just see what happens for t, which is phi1 of y. So if I start going up, so I want to show you where this equation helps. So when I get exactly to the top, when I go from y up to phi1 of y, okay, so if I look at the left-hand side, this one is equal to phi of, so what do I do when I flow exactly to the top? I actually am identified with f of y comma 0. So I come back to the base. So this is this of f of y comma 0. And then I use the definition of my isomorphism. Isomorphism just translates by u of the coordinates. So this is u of f of y, comma, no, sorry, wrong. So f of y stays the same, and I have to translate by u of f of y. Yeah? Okay, so this is just working with the left-hand side. So when I go to exactly for this time, yeah, when I take for this time, when I flow, I get exactly back to the base at this point, and then my isomorphism translates me by f of y. And now I compare with the right-hand side, just to see that I get this cohomological equation. Again, if you want to do a full proof, you have to be careful about this equivalence relation and maybe discuss cases. But I just want to show you the cohomological equation appearing. And now let me do the right-hand side. So just to have colors. The right-hand side is this. So this was the left-hand side. And the right-hand side at this point on the base. So I have to compute phi t2 of, phi of y0, just copying. Phi is, and the t was that I want to consider as phi1 of y, for t, which is phi1 of y. Then this is phi 2 of phi1 of y of, let me imagine that I haven't reached the top yet. Again, otherwise you have to translate it back to the base. Say that this is less than phi2 for a second. Say that u is small, so I haven't gotten to the top yet. And then what do I have to do? So I am in phi2. I start at some y at some height, u of y. And I can flow until I reach the top and then continue for a bit. So to reach the top, I need phi2 of y minus u of y. So this is what is left to get to the top. And then I have to flow for phi1. So let me also assume that this is less than phi1. But again, it's not that. You can deal with all of this by using the equivalence relation more than once. But I don't want to do the general discussion. So you see now I have to flow for to go to the top. I have to flow for this difference, phi2 minus y, and then I'm left with something. So I will write like this. I will write phi2 of phi1 of y minus phi2 of y plus u of y of, and when I get to the top, this goes to f of y, and this goes to 0. So first I flow what brings me to the bottom, to the base. And now I still have to flow by this amount. And again, I'm assuming that this is not yet at the, it's a special case, but if I'm not yet to the top, maybe it's going to be this. And then here I have phi1 of y minus phi2 of y plus u of y. This is what I wanted to get. And now you see, if the right-hand side has to be equal to the left-hand side. Let's look at the right-hand side and the left-hand side. One side was this, and the other side was that. And you see that they both have f of y, so I finally find that this has to be equal to that. Here I have u composed with f, and here I have the difference. So I hope that 1 and 2 are correct. So I need, I don't know. So phi1 minus phi2 to be equal to, at y, to be equal to u composed with f minus u. Is that no, maybe we had the other one. We had the one, yeah. Well, too bad. I changed 1 and 2. It's okay. We had 50-50 chance. So this is just to convince you that the cohomological equations appear from time changes. And maybe digression on cohomological equations in dynamics. So So let me write homological equation again. So again, the question is given f. Maybe now let me write x, because I don't want to keep this y. Is annoying. F from x to x and phi from x to r. Does there exist u from x to r such that u composed with f minus u is equal to phi? So this is the homological equation. And I want to maybe say, just as a comment, this is one form of homological equation. You can, people also call homological equation something with, this is the simplest discrete, but then there is something called a twisted homological equation, where you also have a parameter like this, lambda u composed with f minus u is equal to phi, and lambda is here is the real parameter, it's a twist. So this would be for lambda is equal to 1, and then you have a continuous time version. So this is for a map. So if you have a flow generated, a smooth flow on a smooth manifold generated by some vector field x, then you can look for, so you given a function from x to r, does there exist u from x to r? And this is like a discrete version of just this equation, x of u is equal to f. So is this function a derivative of u? So this is also called homological equation, and it's the continuous time. So I'm looking for when a function is a derivative. And you should think of this homological equation as a discrete difference, kind of a discretized version of a derivative, if you want. So, okay. So if in your life you hear about homological equation, these are all examples of things that people call homological equations. You may see it in the continuous form. But homological equations appear in dynamics in plenty of situations. So, okay, today we saw it is related to triviality of time changes. So, but also in linearization questions, so also in elliptic dynamics, in KAM theory, you can linearize some conjugacy equation and get the Diophant homological equation. Or it's also in questions in hyperbolic dynamics about rigidity or perturbations or stability, and you can get twisted equations. And okay, and this is again a bit of a digression to place it in the word. So in the hyperbolic, okay, how are we doing with time? We have half an hour. So okay, maybe I will make some small comments. So if I want to solve this equation, so there are obvious obstruction. So I'm sticking now to the standard one. To the other ones were just digression. So if I just want to solve the standard homological equation, okay, so maybe what is obvious? Oh, so there are some necessary, by obstruction, I mean, there are some necessary conditions on phi, which if they're not satisfied, I cannot find the solution. So let's look at this equation. So if phi is a coboundary, so one type of obstruction, for example, so if x is a periodic point, i.e. fn of x is equal to x, and I have a solution, then I can sum my function phi along the periodic orbit. So I can sum from 0 to n minus 1 phi of fk of x. So if I look at the sum of phi up to, and if if you have a solution, so if you have then this is a telescopic sum on the other side. This will be the sum from 0 to n minus 1 of u composed with fk plus 1 of x minus u fk of x. So this is telescopic. And then these terms cancel out, but the last and the first. So I have fn u of fn of x minus u of x. All the others cancel out. And this, if the point is periodic, this is equal, so this is 0. So this is an example of it's called a periodic obstruction, right? So it's, yeah. So every periodic orbit, this gives you an obstruction to solve this equation. And in the hyperbolic world, if you have if f is a hyperbolic, then essentially this is essentially the only ones. So somehow there is all this Lifshitz theory, and there are many results that tell you as long as these constraints coming from periodic orbits are satisfied, you can solve the cohomological equation. So the hyperbolic world is, OK, you have to deal with periodic orbits because they exist in the hyperbolic world always, but yeah. OK, but somehow if we go to elliptic or parabolic, the flows of which we want to consider are typically uniquely ergodic, or we don't have periodic orbits, so we do not have to worry about periodic orbit. But there are other obstructions that we have to worry about. So maybe let me, and you can think of a periodic orbit as a special case of an invariant measure. So I can put a delta measure along a periodic orbit. So more in general, if I don't have periodic orbits, but I have some invariant measure, so maybe this was a obvious obstruction. This was 1. And obvious obstruction 2. Obvious obstruction 2 is if mu is an invariant measure, okay, maybe a smooth invariant, not atomic. If it's atomic, we go back to that case. But if I have an invariant measure, then the integral of, so what was my function? Phi composed with f in d mu. Essentially, invariant is by definition means that this integral doesn't change when I compose with f. So the integral, this is invariant measure, means say phi should be at least measurable. Okay. So then I can integrate my equation on the right and on the left. No, sorry, I did it wrong. I want to do this for u. I'm sorry. I want to integrate u. Okay, sorry. I want to integrate u. Then integrating, sorry that I changed board, integrating CE on both sides, I get that the integral of phi in d mu is the integral of u composed with f, sorry, I'm going too slow, minus the integral of u in d mu. And these two are equal, so it has to be mean 0. So this is trivial obstruction. This has to be mean 0. And now we have to do another baby case. So OK, we saw in hyperbolic world, it's periodic orbits, which are important. In elliptic world, often essentially this is enough. This is the only obvious obstruction. For example, let me take as a function irrational rotation. So and my space is 0, 1, or maybe let's write R mod z. And this is R alpha of x is x plus alpha mod 1. Okay. And OK, this is, again, educational if you have never seen it. So imagine that I want to solve the cohomological equation. And what I claim, and I'll show you, is that, so for example, if phi, okay, maybe I should have said it earlier. So all this cohomological equation, the game is always to put some regularity assumption on the function and look for a regular solution. So maybe, so you can do it for measurable. So you can take a measurable function and look for measurable solution. Or you can take, I don't know, C infinity and look for C infinity. Or you can take CK and look, maybe there is what's called loss of regularity. So you look for some U, which is KL for some L. So there are lots of variation of this problem. So let me do for the rotation, you can take, I don't know, have you seen this or not? I don't know. So if phi is a trigonometric polynomial, I'll show you this proof because it's just educational. But so then I claim that you can always solve. So CA has always solution for, okay, mean 0. This is clearly, in this case, the invariant measure is Lebesgue, so it has to be integral 0. But if alpha is irrational, and the function is mean 0, we can solve it. Okay, maybe let's just do. So we can write, we can just do Fourier series, and that's useful because we'll do it in a second in a parabolic case. So I'm just to write this as a trigonometric polynomial, so I'm just going to write it as sum from, okay, maybe now let me do it in, sorry, instead of doing it for trigonometric polynomial, so let me just say one more thing, and then I'll do it in both cases. If phi is smooth, on the other hand, then, and means 0, you can solve it for, with U smooth, for almost every, maybe not for every rational, but for almost every alpha. And this, if you like, the Diophantine approximation. And this, you actually need the Diophantine condition on the rotation number. So in elliptic dynamics, essentially, you often have the Diophantine condition. So let me try this case. So if it's smooth, it's L2, say, and we can write sketch. And I think it's educational for what we're going to do next. You can use Fourier series. So I can write my phi as the sum in k and z of some Fourier coefficients. I call them phi k, e to the 2 pi I k x. Sorry, phi of x. So I write my function in Fourier series, and I look for a solution in Fourier series. So I try to solve it in Fourier series, and I call UK the coefficients. So I'm given this function, and I'm looking for a solution. Okay, and I also know that the 0 coefficient is not there because it's mean 0, so I remove 0. So when I compute U composed with the rotation, I have to plug x plus alpha. So the Fourier series will be UK e to the pi I k x plus alpha. Mod 1 doesn't go. So this is e to the 2 pi I k alpha that multiplies e to the 2 pi I k x. Okay, so I'm going, okay, I continue here because I don't want to change side. So I want to equate Fourier coefficient. So if I look U compose R alpha x minus U of x, the Fourier series is e to the 2 pi I k alpha minus 1 times e to the 2 pi I kx. Okay, and alpha is irrational, so this is non-zero. And now we can do the two cases. So if I have finitely many terms, if it's a trigonometric polynomial, so what do I want? I want this series to be equal to the series for phi, so I want phi k to be equal to e to the 2 pi k alpha minus 1 times uk. I forgot uk. Yeah, so it's an equation between Fourier coefficient. So if I have, if alpha is irrational, I can solve. So I need uk to be phi k e to the 2 pi I k alpha minus 1. So again, alpha is irrational, so this is non-zero. So this is what the solution should be, Fourier coefficient by Fourier coefficient. And so if alpha is irrational, I can always do it. And if phi is a trigonometric polynomial, I have finitely many Fourier coefficients, and that's it. I'm done. If phi is smooth, equivalently is infinity. Equivalently, you have the Fourier coefficients decay super polynomial, so faster than polynomial. It's a if and only if. And okay, so these are the Fourier coefficients of u. But if you want u to be also smooth, you also need the Fourier coefficient to decay super polynomially. And there is an issue. This is called the small divisor. You have to be careful that if alpha is very close to a rational number, this could be very small, and could 1 over this explodes. So maybe your UK don't decay too fast. So in this case, if you want UK to decay fast enough to be Fourier coefficient of a smooth function, you need what are called Diophantine conditions. So you need to assume, for example, that e to the 2 pi I k alpha minus 1 is greater than some, it's not too small. For example, something like this. So, and this is somewhat equivalent to a Diophantine condition on this rotation number, so that it doesn't kill the, okay. Now this was digression, but we're going to use the notation also now. So it was also digression. Okay, so now finally I want to move to a parabolic example. So philosophy, nevertheless, that hyperbolic and elliptic word, okay, you can, most of the time, you can solve cohomological equations. So, okay, maybe here you have Diophantine condition appearing, apart from the trivial obstruction of mean zero. Here you have condition on periodic points. But so what is special of the parabolic word is that there are actually new obstructions, which are neither periodic orbits obstruction nor this invariant measure obstruction. So maybe I will write before we do the example. So parabolic word, and this makes also parabolic word special. There are more obstructions, which are neither so they are not also obstructions. So in addition, okay, periodic orbits we will not worry, because we will not have in our unique body. So, okay, in addition to invariant measure. Let me write an, okay, periodic orbital, if there are. Typically not. And these are invariant distributions. And I want to give you a very concrete examples. Okay. And these sometimes are finitely many, sometimes they are but finitely many, but more than one. But sometimes they are countably many. OK, so example. And the example that I want to do is related to Heisenberg-Neal flows that we saw last week. But I want to, even if you didn't see the lecture last week, I want to, so I will take just a special flow picture. Maybe I should call it, OK, let me take X is T2, and F, which is what we called last week F alpha beta of xy. So X is, point is xy. So this is Furstenberg's Q product that we saw last week. And I'm going to take, this was x plus alpha, so it's a rotation in this coordinate. But and then there is this y plus x plus beta. So do you remember this map from last week? So, OK, and let me recall that we saw that Heisenberg-Neal flows, every Heisenberg non-uniquely ergodic Heisenberg-Neal flow is a special flow over a map F of this type for some alpha beta. We did this exercise of computing explicitly alpha and beta according to which generator of the Neal flow I have. Special flow over F under some, it was under a constant roof function. OK, so if I want to, and last week I studied time changes of Heisenberg flows, and I told you if the time change is not smoothly trivial, no, not trivial, I can prove that the time change is mixing. So, but how do you really produce non-trivial time changes? So I want to investigate this triviality of time change question in this setting. So I need to, from the lemma that we saw before, so I need to study, OK, this is a motivation, to study the cohomological equation. Study the cohomological equation phi is equal to f, so u composed with f minus u for, and I will take phi smooth. Oh, we have got it smooth, so let's say C2 as infinity of T2. And I will say, OK, if I'm interested in non-smoothly trivial time changes, I want to say, does there exist? I want to take phi smooth and look for u smooth. Does there exist a u smooth solution? So I do it in the smooth setting. I start from a smooth function because I'm interested in smooth time changes, and I want to prove if there is or not a smooth solution. OK, the motivation is from last week, and maybe I'll connect it to last week tomorrow. But OK, so does there exist a smooth solution? So the answer is actually there are countably many conditions. It's not enough to have mean zero, but essentially, Furstenberg's Q product. And let me assume that it's also here that alpha is irrational, so that it's uniquely ergodic. So alpha is irrational. This map is uniquely ergodic, and OK, we'll assume that phi is smooth. So this is Lebesgue, dx dy is equal to 0. But it's not enough. It's not enough to solve it. So maybe I will write proposition, and this is Katok already in the 80s, and it's the first cases of invariant distributions which were discovered for parabolic systems. You actually can solve it if and only if countably many additional obstructions are satisfied. Sorry, I need to find how to erase it. And I will write them in Fourier series explicitly. Sorry, very strange sound. So now I have to find the notes, because this I cannot tell you by heart for sure. The expansion, I'm sorry, I need to do this. Yeah, here, Katok. Yes, so I think it's like this. So if phi, so let's write it in Fourier coefficients again. Write phi is a function of xy. So Fourier coefficients are on T2 now, on the two-dimensional torus. So I am assuming that it's smooth, so I can write Fourier coefficients. So it's sum in nm in Z2. And then I have Fourier coefficients mn e to the 2 pi I nm nx plus my. So so the homological equation has a smooth solution if and only if. So there are some distributions indexed by two parameters, n and m. So if and if these distributions are equal to 0 for every m and n in Z2, where, and I think I'm realizing that I'm running out of time, so maybe I will have to, I start today, but I'll continue tomorrow because I feel I'm running out of time. Okay, so so what are these distributions? D and M. So I will write what it's a distribution, so I just have to linearly, I can just tell you define them on Fourier coefficient. So sorry, maybe I will. So okay, I can write it like this. I just have to define them on Fourier modes, ax plus by, where a and b are integer. So I just tell you what is the value of this distribution, and this is equal to, so if it's only picks up if AB is equal, it has this form, n plus k m comma m. It's something that I will write. It's a 0 otherwise. So this distribution is 0 on all Fourier coefficient, on all Fourier modes not of this form. And if the Fourier AB has this form where k is in Z, then I have e to the minus 2 pi I alpha n plus beta m k plus alpha m k over 2. Okay, it's quite a surprising thing. So where does this come out? Okay, so these are countably many. I want to explain where this comes out. Countably many in obstructions, distributional obstruction. And if you remember, so I think it would be silly for me to try to prove this lemma right now. So maybe what I should do is to start with this tomorrow. So first thing tomorrow I will prove. So now you will be left with the mystery. But It's okay, but if you remember last week, I gave you some explicit examples of time changes of Heisenberg flow, which were mixing. And actually, the way that it was some sine or cosine or some combination of sine and sine. And these examples are given by testing. So if you test on this example, this invariant distribution, so you show that some of them are non-zero. And if you, so maybe this is silly, but okay. So if the nm of f is different than 0, for some mn, if you find one of them which is non-zero, then the time change given by this new time change with roof phi is not trivial. It's not smoothly trivial. So it's not trivial in the sense that I cannot solve the cohomological equation with smooth U. So this is an obstruction to solve the cohomological equation. Okay, so maybe given the time, I suggest, yeah, so this looks like out of the blue, but we'll do tomorrow the exercise, and it's an exercise in Fourier series. And some sense like this, I have to act with the dynamics on Fourier coefficient. And from searching from a solution, we will see these expressions popping up. So this will be an exercise in Fourier series tomorrow. So OK, so this is the only example of invariant distribution that is kind of elementary to compute. It's Katok, but somehow this idea that there are invariant distribution has been pushed, especially by Flaminio and Forni. So they found countably many invariant distributions for other nil flows. And for the horocycle flow, you can find the countably many obstructions to solve the cohomological equation. And for area-preserving flows, you don't have countably many, but you have G obstructions where G is the genus. So somehow it's a common feature of parabolic dynamics that this cohomological equation has obstructions. So typically, if you pick at random your function, you cannot, you get something which is not, not a solution. So yeah, so OK, I don't know. So tomorrow I'll do this, and then I'll go back to more geometric idea of shearing and tell you some other consequences of shearing other than mixing that we saw last week. So the last thing I want to talk about is Ratner property of shearing. I want to mention Ratner property of shearing tomorrow, and it's another feature which I think is important in parabolic dynamics. OK, thanks.